Hello and welcome to the stoichiometry video lesson. So stoichiometry in its most basic form involves comparing amounts of two different chemicals during a chemical reaction. And in order to compare amounts of those two different chemicals, we need a balanced chemical equation. Now hopefully you guys are all already masters of balancing chemical equations because of the last video lesson. But once we have our balanced equation, this tells us our ratios of our chemicals in the reaction. So in our example question, we're asked how many moles of iron are needed for a reaction of 12.0 moles of O2. So we're going to set up conversion factors, good old conversion factors, 12.0 moles of O2, and we grab this ratio right here directly from the balanced equation. So we see that there's 3 moles or 3 units of O2 for every 4 moles or 4 units of iron. And the moles of O2 go on the bottom, so they cancel with these moles of O2. And then we perform our math and we end up with 16.0 moles of iron. So we've now compared the sort of amount of moles of two different chemicals in a reaction. In another example right here, we're asked how many moles of CO2 can be produced when 2.25 moles of propane react according to the following balanced reaction. So once again, we need balanced equations, and they're being nice enough to give us balanced equations here, but on a quiz or exam, I'm probably going to give you unbalanced equations. So anyhow, we are going to look at our balanced equation right here. We're going to compare amount of propane to amount of CO2. And we're told we have 2.25 moles of propane, so there's our starting amount. And here's our ratio from our balanced equation. For every 1 mole of propane, that corresponds to 3 moles of CO2. In performing our math, we end up with 6.75 moles of CO2. So I'd like you to now pause the video and please complete question number 1 on the activity. Welcome back, everyone. Let's take this a couple steps further. So now we're going to look at stoichiometry involving mass-to-mass comparisons. So we'll be going through our moles-to-moles comparison as we did before, but we're going to have to use our molar mass to convert in and out of moles. So our first question here is how many grams of CO2 can be produced from 54.6 grams of C2H2. So this is actually acetylene right here. It's a gas commonly used in welding. So here's our balanced equation. As mentioned before, you'll probably be balancing equations on the exam, so make sure you know how to do that. But we can see that we have 2 moles of acetylene for every 4 moles of CO2. So starting out with our grams of acetylene, we have to convert that to moles. So we're going to use our molar mass right here. So this again is our sum of the masses of 2 carbons and 2 hydrogens, gives us that 26.0. And this is set up on the bottom of our ratio, so it cancels out with these grams over here. That's our mass for 1 mole. Then we're going to now use our balanced chemical equation, just like we did in the previous problems. For every 2 moles of acetylene, that's going to be 4 moles of CO2. So notice we've set up the moles of acetylene on the bottom, so they cancel with these moles of acetylene. And then finally, we're going to use our molar mass to convert from moles of CO2 into grams of CO2. So this is the mass of carbon plus the mass of 2 oxygens, gives us that 44.0 grams. And we crunch all of these numbers and we end up with 185 grams of CO2. So I want to point out this might look like a big scary equation right here, but we tend to use these same 3 steps over and over and over. So anytime we're asked to compare from masses of 2 different chemicals in a reaction, we're always going to follow the steps molar mass, balanced equation, molar mass. Molar mass, balanced equation, molar mass. So once you get the hang of it, these problems actually aren't that hard to solve. Well, with enough practice, that is. So let's take a look at another practice problem. Determine the mass of ammonia that can be formed from 62.3 grams of N2. So here's our balanced equation. We always need a balanced equation to solve any stoichiometry problem. And then from there, we're going to use our molar mass, balanced equation, molar mass, just like I talked about before. So 62.3 grams of N2, 28.0 grams of N2 for every 1 mole. There's our molar mass. And notice it's 28 and not 14 because there's 2 nitrogen atoms in an N2 molecule. And so then we have our balanced equation now. For every 1 mole of N2, that's going to make 2 moles of ammonia. And then finally here we have our molar mass again. For every 1 mole of ammonia, that's 17.0 grams. That's our mass of the nitrogen and our 3 hydrogens. And so crunching all our numbers, we end up with 75.7 grams of ammonia being formed from that starting amount of nitrogen. So please pause the video and try and solve question number 2 in the video lesson activity. Welcome back, everyone. Let's take stoichiometry one step further. Let's talk about limiting reactants. So limiting reactant is whichever one of our reactants runs out first. And so what we see is usually one of our chemical reactants is going to run out before the other reactant, and our reaction is going to stop when this occurs. So they give this kind of fun and silly example of if we're making peanut butter sandwiches. Let's say that we have 8 slices of bread in 1 jar of peanut butter, and let's say that our sandwiches are defined as being 2 slices of bread and 1 tablespoon of peanut butter. Once we've made 4 sandwiches, we're out of bread and our sandwich making reaction stops. It doesn't matter how much peanut butter we have left. Once we're out of bread, we can't make more sandwiches. Alternatively, let's say we have again those same 8 slices of bread, but now we have only 1 heaping tablespoon of peanut butter. We can only make 1 sandwich before we're out of peanut butter, despite the fact we have all of this white bread left. So once one of our reactants runs out, it doesn't matter how much of the other one we have left, the whole reaction grinds to a halt. So how do we do the math? Well, bad news is it's like 2 stoichiometry problems. The good news is, hopefully you guys know how to do stoichiometry problems now. So we're asked how many grams of carbon monoxide can be reduced from a mixture of 70 grams of SiO2 and 50 grams of carbon. So here's our trusty balanced equation that we need. And now we're going to set up our unit cancellations. We're going to go molar mass into moles, and we'll do the molar mass again later on. But we're going to figure out how many moles of product we can form from our 70 grams of SiO2 using our molar mass and our balanced equation ratios. And we have enough SiO2 to form 2.32 moles of CO. We don't know if that's actually possible, though, because we have to figure out how much the carbon we'll be using. So essentially, we take our 50 grams of carbon, we use our molar mass and our balanced equation again, and we end up with 2.77 moles of CO being produced. So which one do we actually make? Always the lesser amount. Once we've produced this 2.32 moles of CO, we're completely out of SiO2 and the reaction stops. Even though we have excess carbon left, we can't make any more CO because we're out of our other reactant. So 2.32 is the amount of moles we can actually produce. So now we're going to use our molar mass once more, our 2.32 moles of CO, and then our molar mass of CO right here is 28 grams per mole. And it turns out we can only actually produce 65.0 grams of CO before our reaction stops. So it looks big and complicated, but it's the same thing we did before, except we're essentially applying it twice. Let's take a look at another example problem. If 48.2 grams of calcium are mixed with 31.0 grams of N2, how many grams of calcium nitride can be produced? So here's our balanced equation. And again, on exams, you'll be balancing your own equations. But we're going to take our grams of Ca, use our molar mass, and our balanced equation to determine that we are going to have 0.402 moles of calcium nitride being formed by that amount of calcium. Let's see if which one limits us. So essentially, if we take our 31.0 grams of N2, use our molar mass and our balanced equation, we have enough N2 to produce 1.11 moles of calcium nitride. So how much do we always produce? Once again, it's always the lesser amount, the 0.402 moles of calcium nitride. And once we've produced that lesser amount, we're going to use our molar mass to convert that to grams here. 59.6 grams of calcium nitride will be produced from our mixture here. And our calcium will run out, we'll have excess nitrogen, but the reaction stops when the calcium runs out. So please pause the video and complete question number 3 on the activity.